So section 6.2, this is the unit circle and circular functions. In this section we get to, this is like a culmination of almost everything that we have talked about so far in Module 1. So we're going to combine all of those skills that we've already talked about, and we're going to find the following function values. Example 1, we want to find cosine of 7 pi over 4 and sine of 7 pi over 4. So we've done problems like this, but we just haven't done them in radians yet. So I'm going to start by converting my 7 pi over 4 into degrees. So 7 pi over 4, multiply that by 180 over pi, and that gives me 4 goes into 180, that would be 45, and multiply by 7. Alright, of course pi cancels out, so that's 315 degrees. So I've done problems already where I've had to find cosine of 315 degrees. I know how to handle that. To do a problem like this, we want to find the reference angle. So the reference angle for 315 degrees, let's see, 315 degrees is going to put me in quadrant 4. And then to get my reference angle, I need to do 360 minus 315. And that gives me 45 degrees. Okay? And then all silver teacups. Let's see, all silver teacups, this quadrant 4 is positive for cosine and secant. So this is going to be a positive answer. And so we can do cosine of 315 is equal to cosine of 45. And then cosine of 45, that's one that we should have memorized from the first quadrant of our unit circle. Cosine of 45 degrees is square root 2 over 2. Okay, so that means cosine of 7 pi over 4 is also a positive square root 2 over 2. Alright, and then we need to find sine of 7 pi over 4. That is equal to the sine of 315 degrees. And then that is equal, the reference angle we found to be 45 degrees, but remember 315 degrees is in quadrant 4, and sine is going to be negative in quadrant 4 because it's all silver teacups. Sine is positive in quadrant 2, negative in quadrant 4. So we can say that this is the negative sine of the reference angle was 45 degrees. And sine of 45 degrees we know from quadrant 1 of the unit circle, that's square root 2 over 2. But ours has to be negative, so it's negative square root 2 over 2 is our answer for the sine of 7 pi over 4. So again, it's the same thing that you did in section 5.3, I believe, except now you're just converting your radians over 2 degrees. And there are multiple different ways you can do these problems. We can check these with the unit circle. And looking at the unit circle, if you locate 7 pi over 4, you should find that sine and cosine match our answers here. The only issue is that you can't use this, you won't have the, you don't always have the unit circle to refer to, so you need to be able to do it without looking at the unit circle. Alright, so let's go into example 2. In example 2, we need to find sine of negative 2 pi and tan of negative 2 pi. Alright, so where is 2 pi on the unit circle? Let's look at it real quick. Remember, you're starting here at 0, and when you, this is negative, so you're going to actually be going in the clockwise direction. But negative 2 pi is where you're made a full rotation and you're back to your starting point. So negative 2 pi is the same thing as 0. So you can say sine of 0. Alright, and what is sine of 0? Well, if you're right here, the ordered pair would be 1 comma 0. So your sine value is 0. What about tan of negative 2 pi? Well, that's going to be tangent of this same point, and we know when we do tangent, we do y over x, so 0 over 1, and that's also 0. So that tells us that sine of negative 2 pi is equal to 0, and tan of negative 2 pi is equal to 0. Alright, so there are multiple different ways to think about this problem. If there's another way that makes more sense to you, then you can, that's fine too. But at any rate, because negative 2 pi is the same thing as 0, then I'm just finding the sine and the tangent of this point right here on the unit circle. Alright, example 3, we are finding, let's see, cosecant of 11 pi over 6 and cotangent of 11 pi over 6. There's example 3. Okay, so on this one I'm going to start by converting my radians into degrees. So 11 pi over 6, multiply that by 180 over pi. So 6 goes into 180, that's 30. And then pi cancels, so I get 330 degrees. So I'm just simply asked to find cosecant and cotangent of 330 degrees. Okay, and this is a problem that you've probably already done before. So if you recall, when we did these problems in the past, we wanted to find the reference angle for 330 degrees. Okay, so there's 360. I'll go all the way around into quadrant 4, and there's the angle. My reference angle would be 360 minus 330. That's going to be 30 degrees. Reference angle is 30 degrees, and what about the sine? All silver tea cups, C means cosine. So cosine is positive, and secant is positive, but everything else is negative. So that means that cosecant is going to be negative. So cosecant of 330 is equal to the negative cosecant of my reference angle, 30. And then that would be negative cosecant is 1 over sine. So I've got negative 1 over sine 30. Okay. And that equals negative 1 over, what is sine 30? Okay, here's another one that we're supposed to have memorized. If you don't have it memorized, you can still figure it out. Go to your unit circle. This is 1, 0. Alright, 30 degrees is the next one up. And the ordered pair here, following the pattern, is square root 3 over 2, comma 1/2. So I want the sine value, so I want the y coordinate, so that's 1/2. So negative 1 over 1/2, and that's going to be the same thing as negative 2. So cosecant of 11 pi over 6 equals negative 2. Alright, what about cotangent? So for cotangent, we're going to do cotangent of 330 degrees. That's equal to, the reference angle I know is 30 degrees. What about the sine? I'm in quadrant 4. All silver tea cups. Tangent is negative in quadrant 4. Tangent's positive over here in quadrant 3. So it's going to be negative cotangent 30 degrees. And that is equal to negative 1 over tan of 30. That's equal to negative 1 over, we're supposed to know tan of 30. Tan of 30 is square root 3 over 3. Equals, and that's going to be negative, do the reciprocal, so negative 3 over square root 3. Rationalize your denominator. Your answer is negative 3. It's negative 3 square root 3 over 3, or negative square root 3 when you simplify it. And that's cotangent of 330. So I'll try to write this in. Cotangent of 11 pi over 6. Out of space here. Cotangent of 11 pi over 6 equals negative square root 3. Okay, and that's how you do that one. So we first need to make sure our calculator is in radian mode. So on your calculator, go to mode, and mine is in degrees, so I've got to highlight radian, press enter, and then I can second quit to go back to my regular screen. In example 4, find a calculator approximation for the following around to 4 decimal places as needed. So this is just a matter of typing this directly into your calculator, nothing special going on here. Okay, so alright, so sine of 0.5348, and they said round to 4 decimal places, so that's giving me 0.5097. Tan 3.4865 gives me 0.3593. Secant of 2.7165, I get that by doing 1 over cosine 2.7165. That's giving me negative 1.0977. Okay, and that's it for that. There was an extra space here. That you could have written, it was 1 over cosine 2.7165. That was what I didn't write in. Okay, so those were just a matter of typing them into our calculator. Same with example 5. Find a calculator approximation for the following in the interval from 0 to pi over 2. Alright, round to 4 decimal places is needed. Okay, so what we're going to do here, we've got sine of s is equal to this. Alright, so we're going to take sine inverse of both sides, and that'll be s equals sine inverse 0.9634. We'll type that into our calculator. So I'm going to go second sine to get to my inverse function, 0.9634. That gives me 1.2994. Okay, and for part B, cotangent, I do get that by well, excuse me, I'm going to do sine inverse, I'm sorry, I want to take the inverse cotangent of both sides. Now before I do that though, I need to rewrite my cotangent as my reciprocal 1 over tan. So this is 1 over tan s equals 0.2994. So that means that tan of s equals 1 over 0.2994, and then I'm going to do the inverse function. So tan inverse, so second tan, and then put in 1 over 0.2994. I'm getting 1.2799. Or let's see, that would actually round up to, yeah, that's right, 1.2799 for that one. Okay, so it's always nice when you see one that says use a calculator approximation, because you get to type it straight into your calculator. However, you have to be really careful with these inverse functions because they don't always, your calculator does not always give you what your we have to be really careful with domain and range of inverse functions. That can get a little sticky. So long story short, what I'm saying all up here is that unless your calculator specifically tells you to do the decimal approximation using the calculator, I'm sorry, I don't know. Let me say that again. In case your directions specifically tell you to use a calculator approximation, you need to avoid the calculator for these inverse functions, because you can get you can miss possible answers that you need, or you can get the wrong answer. Just depending on the domain that you're given for the problem. Okay, so your calculator cannot help you as much, so it has limitations. Long story short, what this is saying is that if you're finding cosine of inverse, your answer would only be in the first or the second quadrants. If you're finding sine inverse, your answer is only in the first or the fourth quadrants. And when finding tan inverse, your answer is only in the first or the fourth quadrants. Okay, so it is possible that your calculator could give you answers that are not in the correct quadrants. So unless you are specifically told to use the calculator, don't use the calculator. Okay, in the next set of examples, we want to find the exact value of s in the given interval that has the given circular value. Be careful in problems like this. You are doing the inverse cosine of this in order to solve for s, but you've got to be extra careful about typing it into the calculator. Depending on how the domain is defined, the calculator may or may not give you the correct answer. So we are going to kind of do this by hand. So we're going to start by looking at what quadrant we're in. We're in the interval from pi over 2 to pi. So where does that put us on the unit circle? Alright, so here's 0, and then that would be pi over 2, and then this is pi. So this would be pi here, and pi over 2. So from pi over 2 to pi, it means we're in quadrant 2. So we're going to be somewhere in here. Now, cosine of s is negative 1/2. Let's ignore the negative for a moment and just think about the reference angle, cosine r equal 1/2. We should be able to figure this out from what we know about our unit circle. Cosine of what equals 1/2? Think about your unit circle. You might remember, but so you remember we've got 1, 0 here at 0 degrees, and then at 30 degrees is going to go, that would be square root 3 over 2, comma 1/2. When is the cosine 1/2? Well, it's going to be, cosine is going to be 1/2 at 60 degrees up here. So r is 60 degrees. So this, again, this is what you memorized in quadrant 1 of your unit circle. Cosine 60 equals 1/2. All right. So so we have reference angle of 60 degrees, and we know we have to be in quadrant 2. So what does that make our angle equal to? Well, we got 180 degrees, and then the reference angle is 60 degrees. So 180 minus 60 is 120 degrees. So the angle we're looking for is 120 degrees. They want us to find the exact value of s. Okay, so we found it in degrees. Now we need to give it in radians. So if I convert 120 degrees into radians, so multiply it by pi over 180. That's going to give me 2 pi over 3. So s is equal to 2 pi over 3. Okay. Example 7 is the same directions. We're finding the exact value of s in the given interval that has the given circular value. Now this time my interval is 3 pi over 2 to 2 pi. So what quadrant is that? Okay, so this is pi over 2, that's pi, that's 3 pi over 2, this is 2 pi. So I'm in quadrant 4. That's 3 pi over 2, and that's pi over 2, and this is 2 pi. Okay, so I'm in quadrant 4. Sine of s is equal to negative square root 3 over 2. Let's do our reference angle first. Sine of r equals, and you can just drop the negative, square root 3 over 2. Now, sine of what is square root 3 over 2? Hopefully you've got it memorized, but if you don't, draw your picture. Alright, there's 1, 0. And then the next one is square root 3 over 2, comma 1/2. When is the sine square root 3 over 2? That's going to be up here at 60 degrees. Okay, so that's 1/2 comma square root 3 over 2, 60 degrees. So R is equal to 60 degrees. Okay, now go back to your picture. You're in quadrant 4. So where is the, what's the angle going to be? The reference angle was 60 degrees. That's the distance from the x-axis to the terminal side of the angle from here to here. I need to find the actual angle itself, so you can do 360 degrees minus 60. That gives us 300 degrees. Okay, and then the only thing left to do is to convert this into radians. So 300 times pi over 180 gives me 5 pi over 3. So my angle S is 5 pi over 3. Okay. Example 8, same thing. Okay, we're starting with the interval from pi to 3 pi over 2. Where does that put us? Alright, that's pi over 2. This is pi. This is 3 pi over 2. So I'm in quadrant 3. This is where my angle is going to be. Now let's find our reference angle. We want tan of R equals square root 3 over 3. This is one that you really need to have memorized. Tan of what is square root 3 over 3? Well, that's tan of 30. Tan of 30 is square root 3 over 3. And, excuse me. So, my reference angle, R, is 30 degrees. And I'm in quadrant 3, so that means S is going to be 180 plus 30, which is 210 degrees. And now I want to convert that into radians, so 210 times pi over 180 gives me 7 pi over 6. So S equals 7 pi over 6. Okay, so this is the way you can do it, by just simply converting what you're given into degrees, working with degrees and converting back into radians at the end. As you become more familiar with, more comfortable with working in radians, you're going to be able to find some shortcuts to make this a little bit quicker. But for now, just do it whichever way makes sense to you. Go with it. As long as you can support your answer and show your work for whatever method you're using, that will be fine. Okay, so that was 7 pi over 6 for number 8. For the applications portion of section 6.2, we're going to be working with angular and linear speed. Before we go into this, let me draw a picture of what that means. So let's say we've got, imagine that's a radius, all right? The speed, if this is like the minute hand of a clock, the speed at which this rotates around is going to be angular speed. So, of course, if it rotates all the way around, it creates a circle. But the speed that this thing is moving like this is their angular speed. Linear speed would be the actual distance that's traveled, let's say from point A to point B, around the circumference of a circle. So the linear speed is how fast you're going around that. Like if you're just walking around this or running around it, that's your linear speed. And we get angular speed is how fast this this radius is rotating around your circle like that. Well, so we've got a definition. Angular speed is the change of radians per unit of time. So angular speed is going to be measured in radians per unit of time. We've got several formulas here. This W equals theta over t, so that means angular speed equals radians over time. And then the linear speed is the change of position per unit of time. Like we said, that's how fast that you're walking along the circumference of the circle. The formulas here are v for linear speed equals distance over time. That's just your distance formula. Distance equals, it's like, well, it's similar to your distance formula. But linear speed is equal to the distance divided by the time. Another way that you can write that is you can say linear speed is equal to the radius times theta over time. This is coming from your distance. Your distance is equal to r times theta. So these are really the same thing. It's just two different ways of saying the same thing. Or you could finally say v is equal to the radius times the angular speed. Okay, so we've got a lot of formulas to keep up with here, but I will probably help you out on the test if you need to. I'll probably kind of point you in the right direction as to which formulas to use here. So let's go on to page 8. So there's several problems in your homework where you'll be manipulating the equations. We're going to just look at a couple of the tougher examples. So in example 9, that says the tires of a bicycle have radius 13 inches and are turning at the rate of 215 revolutions per minute. How fast is the bicycle traveling in miles per hour? They give us a hint that there are 5,280 feet in 1 mile. Now remember, in the definition for angular speed, it was defined to be the change of radians per unit of time. So that means that we need to convert the 215 revolutions per minute into radians per minute. So to do that, we're just going to do a conversion. If you think about it, 1 revolution all the way around the circle, we know that that's 2 pi radians. So we can use a conversion factor, 2 pi radians to 1 revolution. And then multiplying that gives us 430 pi radians per minute. Alright? Now, this gives us our angular speed. We need linear speed. Linear speed, we know, is from the formula v equals radius times theta in radians divided by t. So we'll do 13 times 430 pi all over 1 minute. That simplifies to a linear speed of 5,590 pi inches per minute. Okay, so that's all well and good, but we don't want inches per minute, we want miles per hour. So all we have to do now is convert this 5,590 pi from inches per minute to miles per hour. Okay, so we have another conversion, and we'll see. So we've got the 5,590 pi inches per minute. Alright, we just convert. We know that there are 12 inches in a foot, so inches cross out. And we know that there are 5,280 feet in a mile. And we need to go from minutes to hours, so 60 minutes to an hour, and then we cross out all of the units that cancel, and that leaves us with 16.6 miles per hour. Okay? So that's it. And then we can look at example 10. So in example 10, a pulley has a radius of 12.96 centimeters. Suppose it takes 18 seconds for 56 centimeters of belt to go around the pulley. First find the linear speed in centimeters per second, and then find the angular speed in radians per second. So linear speed, we need to do v equal s over t, that's distance divided by time. So the distance is the 56 centimeters per 18 seconds. That gives us 3.1 centimeters per second. So part A is done. That was pretty easy. Part B, we're doing linear speed, so that's going to be v equals the distance over the time. And we also know that linear speed is equal to the radius times the angular speed. Okay, so we can, this is a little bit trickier, but we're going to set the s over t equal to the r times w. And then that gives us a way of solving for w. So in other words, we know that distance over time is equal to the radius times the angular speed. So we can find our angular speed just by solving this for w. So the distance was the 56 centimeters, the time was the 18 seconds, and the radius was 12.96 centimeters. And solving that for W gives us 0.24 in radians per second. Alright, and that is it. So just a couple of applications of the 6.2 material, but that concludes Module 1. And we will practice these more in class. Thank you.